I start sharing my screen?
Yeah, that's fine.
How can I do that?
Oh, I thought that you checked already.
Yes, but
We're live.
it's... Hi, good morning.
No, I will introduce you. 1 second.
Yes, but oh, now
Hi,
it's
hi everyone. Next, we have Magdalena Stowinska, who is gonna tell us about quantum enhanced interferometry with large heralded photon number states. Magdalena, yeah, perfect. We can see your slide. Thanks. The floor is yours.
perfect. Thank you. Thank you so much for kind introduction and your invitation. It's a wonderful conference, wonderful initiative. I participate with pleasure. Today, I would like to tell you about multi-photon interferometry. That is quantum enhanced interferometry with photon number states, so Fock states. This work has been done in collaboration with the University of Oxford and Imperial College London, and of course the University of Warsaw, where me and my group are based, as well as NIST in the US. So in particular, the work, the credit goes to Guillaume Tekadech from Oxford and Monica Mycroft, my PhD student in Warsaw. The paper has been published in NPJ, Quantum Information, in 2020, and here you can see the QR code if you would like to see more details. So just a short motivation, I don't know, if just so that we all are at the same page. The shot noise limits the precision of measurements. We all know that we can't measure with arbitrary precision objects, especially if we are using classical light. However, this limit can be beaten if we use light with some non-classical properties. And there are two such properties that are mainly explored, namely entanglement and squeezing. And such quantum enhanced precision measurements can be used in various contexts. For example, they may offer an alternative to currently used methods in biology to research really small objects. Of course, it depends on the parameters that we choose, for example, the wavelength and the number of photons, but it looks like one could even reach the sizes of the of cells, or even the parts, the building blocks of cells, with the technology that exists. So the ultimate bound in the interferometry is called the Heisenberg limit. This stems from the fact that we still have the Heisenberg uncertainty relation that holds true, so we can't do an arbitrary precision measurements. However, we can significantly improve the classical capability. And the key resource, maybe not the key resource, but the well-known resource to do that are so-called the Noon states. And in theory, they allow us to achieve this scaling, but they are totally impractical because any amount of noise that goes in, any kind of imperfection that goes into our experiment disrupts this measurement, and the sensitivity drops dramatically in the presence of these imperfections. So it becomes necessary to find states, quantum states, that trade away sensitivity for loss tolerance. And here was born the concept of optimal states that gives the best sensitivity for a given amount of loss in the system. However, and these states have been found, and I will show you in a second what's their structure, but unfortunately it's quite complicated. And that means they would be very difficult to create. And again, we are running into infeasibility if it comes to practical measurements. Let me comment a little bit on the concept of the optimal states. So here we see the graphics that shows the sensitivity of particular states for the phase phase measurement. So we are trying to measure as precisely as possible a phase that the light acquires, so a delay in an optical path that the light acquires if it goes through, for example, not fully transparent medium. And this graph shows only the performances for states with minimal phase uncertainty relations. So these states that can offer the best measurement, the best sensitivity for that kind of measurement. I assume that all of them, they have 10 photons in them, and I investigate what is the performance in presence of losses in one arm of the interferometer. I have in mind the usual Mach-Zehnder interferometer. The red dashed line corresponds to noon states. So as you can see, if the losses are increasing, the sensitivity dramatically drops and very quickly. So we are losing the property. Now the blue solid line corresponds to an optimal state that I will show you in a second. As you can see, it actually it actually behaves much better, and it preserves its properties much longer. There are also two other options, much less, also not very feasible, but that can be considered. That is the dotted green, light green dotted line, which corresponds to optimal two-component state, which is a simple modification of a noon state. Namely, we are adding we are creating a superposition that is not balanced. The dark green dashed dotted line corresponds to so-called noon chopping strategy. So we are throwing noon states of smaller photon number components than n, but we are repeating this experiment a certain number of times, and therefore collectively we achieve some increase in the Fisher information. The shaded area in this graph corresponds to the standard interferometric limit that is achievable with classical states and with the Heisenberg limit 1/n. So we see that although these states work, and in theory, in ideal conditions, they all provide us with very good sensitivity in the phase measurements. If we now take into account the losses in the system, the performance is deteriorating and is different. The performance can be engineered, therefore. This is the example of the optimal states that gives us the hope that still in the lossy measurements, in the lossy conditions, in imperfect measurements, we still can actually reach higher sensitivities levels than in classical situation. This is a two-mode superposition with, of course, entanglement in the number of photons, as we are talking about phase measurements. And the graphic on the left shows us the amplitudes that govern this superposition. So as you can see, this is a very complicated state. The graphics is done for 10 photons, and under assumption that we have losses in just one arm of the interferometer. This analysis comes from the paper that I am giving reference below. But as you can see, the hope that we will on demand generate a particular optimal state is rather low. So what can we do about it? We need to find a way how to approximate these that are available. Let me quickly comment on classical and quantum Fisher information before we proceed with details of our solution. So the ultimate Heisenberg limit corresponds to actually achieving the so-called Kramer-Rao bound, which says that the standard deviation in measurement of the phase is larger or equal 1 over the quantum Fisher information. And quantum Fisher information is a quantity that can be considered a property of our quantum state, and it corresponds to sensitivity that can be achieved under assumption that we have actually chosen the optimal measurement that allows us to do so. And now, in practice, if we now consider classical Fisher information, this is something that we can measure actually in experiment, and we calculate it from a probability distribution that characterizes a specific measurement strategy that we adopt for our experiment. So you can imagine that we are considering a specific quantum state, a quantum resource, and we aim at measuring phase, optical phase. And now we are trying to employ various kind of measurements, and our result, the precision, varies. And if we choose, that is what amounts to classical Fisher information corresponding to this particular measurement strategy. If we now choose an optimal strategy, we arrive at the quantum Fisher information. Okay, so the optimal states, the most general pure two-mode states with definite photon number, which have been optimized to yield the highest quantum information for a given transmissivity. Easier said than done, but it turns out that so-called Holland-Burnett states and the generalized Holland-Burnett states are a very good approximation to the optimal states, to the performance given by the optimal states. What are the Holland-Burnett states? What are the generalized Holland-Burnett states? And why we are talking about them here? It's because we can rather easily produce them in a laboratory. So a Holland-Burnett state, it's a two-mode quantum superposition that is generated by interference of two equal Fock states. This process is shown on the graphics on the left. So we see that there are two n/2 Fock states interfering on a symmetric beam splitter. The output is exactly the Holland-Burnett state. It's a generalization of the Nun state in this sense that except for these extreme components n0 and 0n, there are all other components in between included in the state. So n-1, 1, n-2, 2, and so on and so forth with proper amplitudes. This state is already known to have higher robustness against losses, so offering a bit better performance than the Nun states in presence of small losses. Now, this state can be generalized to the example shown on the right, where the inputs are also Fock states, but they are not equal. Here they are denoted H1 and H2. They still interfere on a 50-50 beam splitter and generate an output that also contains all two-mode components that can be all the components that correspond to the distribution of n photons between two parties, but with slightly altered amplitudes with respect to the Holland-Burnett states. These generalized Holland-Burnett states are actually a family of states. This is not just one state, it's a family of states. And the particular family of states has two parameters that define it. That is the total number of heralded photons, n, which is H1 plus H2, and the difference, delta, the difference at the input, so H1 minus H2. And depending on this difference, we will see that particular members of this family of states offer optimal performance for a given interval of the losses in our system. How do they look like? Here there are exemplary photon number distributions for the generalized Holland-Burnett states. So H1 is the index of the photon number distribution. They are given, the photon number distributions are given by the so-called Kravchuk functions. These are the this is a family of orthogonal polynomials. And as the graphics show below, for n equal 4, we see that depending on the initial imbalance on the entries of the beam splitters, so H1 being not equal to H2, we can generate family members with different amplitudes. So if the difference is maximal, so equals 2 or minus 2, depends how we order, we generate a state that resembles, photon number distribution resembles a binomial distribution, the far left figure. If we now generate Holland-Burnett states with the difference of 1, we see the figure in the middle. If we again put H1 equal H2, we restore our original Holland-Burnett state, and this is the figure shown on the right. Okay, so let us see how they behave, these states, in presence of losses, in the sense what kind of Fisher information per photon they provide. And this is the graphics shown here, computed for n equal 8 photons. So we consider a family of generalized Holland-Burnett states that is computed for 8 photons in total, distributed between 2 modes. The delta equals 0, so the most purple line corresponds to the original HB state, while the delta equal 8 corresponds to the state that actually brings us back to the classical limit for the sensitivity, shown by the yellow line at the value 1. All other states, as you can see, they are very closely resembling the optimal states that are achieved, that are computed for this situation, and shown in dashed lines here. Okay, so depending on the interval of the losses, we can choose what family member to choose in order to obtain the highest Fisher information. We have computed, since this is a little bit troublesome, we have done these computations of the generalized Holland-Burnett states numerically, and compared with the optimal state shown here, the black solid line. Also, we compared to the NUM states, which is the black dashed lines. All the colorful solid lines correspond to the generalized Holland-Burnett states, and as you can see, piecewise, they actually pretty well resemble the performance offered for the optimal states. The quantum Fisher information for these probes takes values very close to these which are obtained for the optimal states. There are assumptions behind these computations, and this is again n equal 8 photons, equal losses in both interferometer arms, and no losses in the heralded modes. So from this, the takeaway message from this figure is that if one is capable of estimating how much losses there are in the system, one is able to identify which family member of the generalized Holland-Burnett states to use to obtain the most optimal performance in the phase estimation measurement. Okay, so yes, this is exactly what I said. Our probes can be tuned to perform close to the most optimal way in any setup, as long as we know what the losses in the setup are. A theoretical scheme showing how to prepare the generalized Holland-Burnett states. I have already mentioned that the states are generated by interference of Fock states, but how to have the Fock states. So we show the scheme where we generate the Fock states in a heralded manner using the standard sources for quantum light, so-called spontaneous parametric down conversion sources. We take two such sources. We produce squeeze vacuum state, two-mode squeeze vacuum state, which are photon number entangled, and we take one beam of each of the squeezed vacua, and, for example, two idlers, and let the two signals propagate to photon-number-resolving detectors, for example, transition edge sensors that are capable of almost perfect projection on a given Fock state, here shown H1, H2. In this way, due to photon number entanglement carried by two-mode squeezed vacuum state that is naturally produced by SPDC sources, we know that exactly the same Fock states, H1 and H2, enter the first from the left, the beam splitter, and interfere to produce exactly a generalized Holland-Burnett states behind that further propagates through the Mach-Zehnder interferometer, in which one arm there is a phase phi located that we aim at measuring. The ultimate measurements that tell us about the results are the projective measurement also performed by transition edge sensors, denoted here S1 and S2. These are also photon number states that we are measuring. In practice, it looked like that. This is the setup that we built in the laboratory of Ian Walmsley at the University of Oxford, and later brought to Imperial College London. In the center of the figure, you see the SPDC source, the periodically poled KTP crystal that produces squeezed vacuum state at the wavelength of 1554 nanometers, so close to telecom wavelength. And then the beams A and D are, the beams denoted A and D are used for heralding, and the other beams are propagated through a variable coupler, which is actually the beam splitter with variable splitting ratio. We did not build specific Mach-Zehnder interferometer with the phase in one of its arms, because this interferometer mathematically corresponds exactly to a variable, to a fiber coupler with variable ratio. So by changing the reflectivity of this integrated beam splitter, we are simulating the various phases, various values of phases in the Mach-Zehnder interferometer. All the measurements are brought to TSs, which are later, the results are later passed to data acquisition and processed on the computer. Importantly, TES detectors reveal quantum efficiency exceeding 90%. Therefore, it is really a photon number resolved measurement. Okay, what are the other parameters of our experiments? The figure of merit in these measurements was the classical Fisher information per signal photon measured. The total efficiency in our system was about 50%, taking into account, of course, waveguide transmission, imperfect mode coupling, efficiency into fibers, interferometer transmission, and detector efficiency, which itself is very, very high. All that was enough to see some trends, but not enough to demonstrate quantum enhanced metrology without post-selection. But let me comment first step by step. So we have generated, we have done experiments in two regimes, weak gain regime and higher gain regime. First, I would like to show you the more interesting results for the higher gain regime, which is more or less the value of parametric gain 0.75. And that meant that we could generate 16 photon events 7 times per minute. Here, the graphics on the left shows us the classical Fisher information that is computed as a function of a specific phase that is in one-to-one correspondence with the reflectivity of variable coupler. That was achieved for the whole family of states, generalized Holland-Burnett states. So we see that if we are, for example, for measuring the phase of pi over 2, delta equal 8 gives the best performance, other states give less great performance. The other two figures correspond to joint probability, photon number probability distributions, and various lines correspond to various combinations of inputs and outputs. So for example, the solid blue line corresponds to measuring behind the Mach-Zehnder interferometer in one arm 8, in the other one vacuum, when assuming that 8 photons in one arm entered the interferometer and the vacuum entered from the other arm. And so on and so forth. We see that various combinations of various measurements give us differing probability distributions according to our predictions. The error bars shown here correspond to more or less one standard deviation, and they are computed with regard to Poissonian noise formula. If we wanted to recover the shot noise limit performance that is obtained for delta equal n, so for the largest imbalance at the entry, we can do that. As you can see, we were able to do that with one source blocked easily, less easily with both sources unblocked. Why was that? It's because of the inefficiencies in the coupling, the inefficiencies in general in the detection system in our setup. We were able to demonstrate quantum advantage if post-selection was used. This is shown exactly in the figures, the panels below, so red and green curves. The green curves show results post-selected on events where the number of photons detected behind the interferometer was equal to the number of heralded photons. The red curves corresponds to the situation where no post-selection was taken into account. The upper figures correspond to the probability distributions that are measured in this experiment, and out of which we later compute the classical information shown below. As you can see, the most of the detection points correspond well to the theoretical prediction in this experiment. Proving a quantum enhanced sensitivity as a result of multiphoton interference, in order to show that indeed this multiphoton component played a role, and it's the enhancement comes from multiphoton interference, we decided to perform a small other experiment where we introduced a small delay in the interference of the photons. So the bold line corresponds to photons injected at the same time, while the dashed line when the photons were injected with a time delay. As you can see, it becomes clear that the multiphoton interference played a key role in obtaining this result. So just a quick summary and outlook. We have proposed and demonstrated experimentally a scheme to produce probes which well approximate the performance of the otherwise complicated optimal states in the whole range of losses in our setup. The scheme is based on two-mode squeeze vacuum sources and photon-number-resolving detection. That was the first experiment that used quantum probes with up to n equal photons. That was the result of 16 photon coincidences observed. With further improvements in the quality of the bright two-mode squeeze vacuum sources compatible with the transmission edge sensors, the scheme provides a promising route towards achieving quantum enhanced resolution using large entangled photonic states. Since this experiment can be also performed in the X-ray domain, our solution could find application in imaging of biological tissues with soft X-rays. Thank you very much for your attention. Monica is shown on the top right corner in this photo. And I would like to take the opportunity to advertise that we are actually happy to employ 3 more postdocs in the group. These are positions that are funded by European projects, Quant-Era projects, in a very interesting area of research as reservoir quantum computing. So please drop me a line if you would be interested in joining our group. Thank you very much.
Thanks very much, Magdalena. Great results there, and good that you are hiring more people. So anyone, just write Magdalena. Thanks a lot. So we are really late on the schedule, so if you can just respond very quickly. We have 2 questions.
Sure.
So the first one from Aurel: is this a scheme that could be suitable for integrated optical solutions? If so, what would be advantages or challenges?
This was done in an integrated manner, almost fully integrated. What was not integrated was actually just the detectors. And the advantages are you can control better the key, the parameter that allows us this result is the fact that the squeezed vacua produced are single mode. If they are not single mode, this interference does not work. So being integrated, we have better control over that. So I think that's the fastest I can.
Thanks. And we have a question from Oleg. Can your method be used in some way for very high number of photons, like in gravitational waves experiments with LIGO interferometry, where photon shot noise is also one of the sensitivity limiting factors with laser power, where the laser power is large?
I think so. It's the matter of adjusting, tuning the detection system, so this transitional sensors, to higher number of photons. But I know it depends how many photons we need. I know they are very working hard on that capability. And if not today, I guess soon. I have information that these detectors can be adjusted to measure about couple of thousand of photons with the sensitivity of 2 photons. So they tell you have, I don't know, 3,005 photons plus minus 2 photons. So it's getting really well, the development.
Perfect. Thanks a lot,
Yeah.
Magdalena. So
Thank you very much.
unfortunately, thanks. We don't have a 15 minutes break anymore. We just have 5 minutes. I just
Sure.
want to take this as an attention for you that whenever you can, just visit the industry booths, that they are there for you. If you have any information, if you want further information, just click on the button
Okay.
to register with them. Again, thanks, Magdalena. Enjoy the rest of
Thank
the
you.
event, and
Enjoy.
rest. See you soon. Bye.
Bye.